Welcome back to Basic Electronics. In this lecture, we will look at a few specific counter circuits. We will start with the binary ripple counter and look at the count up and count down operations. We will then see how a binary ripple counter can be modified to count from 0 to 9 using the direct set and reset flip-flop inputs. Finally, we will look at the meaning of the term synchronous counter and illustrate it with an example. Okay, let us start. Let us now look at some specific counter circuits, and we'll start with this circuit called the binary ripple counter. So here is the circuit. We have JK flip-flops, in this case 3 of them. The J and K inputs are tied together for each flip-flop, and those are connected to 1. So J is 1 here, K is 1 here, J is 1 here, K is 1 here, and so on. The clock, this signal, is connected to this first flip-flop, which we have called as flip-flop 0, whose output is Q0. And the clock for the second flip-flop comes from the Q of the first flip-flop. That means Q0 is connected as clock here. Similarly, Q1 is connected as the clock for the third flip-flop, FF2. Alright, let us now figure out how this circuit works. As we already said, J is equal to K is equal to 1 for all flip-flops, and our starting point is Q0, Q1, Q2 are all 0 initially. Okay, now since J and K are both equal to 1, if we refer to the transition table for the JK flip-flop, we find that after each active clock edge, the output is going to toggle. So therefore, each flip-flop will toggle when an active clock edge arrives. In this case, the active clock edge is a negative clock edge, and that is why we have marked these negative edges here. And we are now in a position to draw these waveforms. Since Q0 is 0 in the beginning, it's going to toggle at this point because there is an active edge there, and the clock is actually serving as the clock for the first flip-flop. So here it will toggle to 1. Once again, when an active clock edge comes, it's going to toggle, go back to 0, then go back to 1, and so on. So that's going to repeat for Q0, like that. What about Q1? For Q1, this Q0 acts as the clock. So now we are looking for a negative edge in the Q0 waveform, and those edges are marked here. So therefore, Q1 is 0 to begin with. It's going to toggle at this time, going to toggle again over there, and so on. So that is what Q1 looks like. What about Q2? Q1 serves as the clock for this flip-flop, and therefore an active edge for FF2 is this edge or this edge. So Q2, which is 0 in the beginning, is going to toggle here and is going to toggle here again, like that. Here is the straight transition diagram for this counter. These are the counter outputs, Q2, Q1, Q0. To begin with, we have 0, 0, 0, then we have 0, 0, 1, then we have 0, 1, 0, and so on. And after 8 states, we come back to 0, 0, 0. And note that this is decimal 0, this is decimal 1, decimal 2, 3, 4, 5, 6, 7, and then back to 0. So the counter repeats after this point. So it's a modulo 8 counter. One final remark before we leave this slide. Note that the direct inputs SD and RD, which are not shown in this picture, are assumed to be SD equal to RD equal to 0 for all flip-flops. And that allows normal flip-flop operation. So that is implicit in this entire description. Let us make a few more remarks. The counter has 8 states. namely Q2, Q1, Q0 equal to 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. Therefore, it's a mod 8 counter. In particular, it is a binary mod 8 up counter since it counts up from 0, 0, 0 to 1, 1, 1. If the clock frequency is Fc, then the frequency at the Q0, Q1, Q2 outputs is Fc by 2, Fc by 4 and Fc by 8 respectively. And that can be clearly seen from this figure here. The frequency of Q0 is half of the clock frequency. Frequency of Q1 is half of the Q0 frequency, and the frequency of Q2 is half of the Q1 frequency. So therefore, we have Fc by 2, Fc by 4 and Fc by 8 for these three outputs respectively. So for this counter, divide by 2, divide by 4 and divide by 8 outputs are already available without requiring any decoding logic. This type of counter is called a ripple counter since the clock transitions ripple through the flip-flops. And that is easy to see. The clock inputs for these three flip-flops are not the same. This one gets the actual clock. The clock for this flip-flop comes from the output of the previous flip-flop, and the clock for this flip-flop comes again from the output of the previous flip-flop. So in that sense, the clock ripples through these flip-flops, and that's why it's called a ripple counter. So it's a binary ripple up counter. Let us now look at a variation of the previous circuit that we saw. Once again, we have three flip-flops, FF0, FF1 and FF2. Their J and K inputs are tied together and connected to 1. The clock, which is shown here, is applied to the first flip-flop. The output of the first flip-flop is connected as the clock of the second one, and the output of the second flip-flop is connected as the clock of the third one. The only difference between this circuit and the previous circuit is that these flip-flops are positive edge triggered, and as we will see, that makes a big difference in the functionality of this counter. Alright, now let us start with Q0. Now for this first flip-flop, the clock signal serves as the clock, and that is shown here, and the active edge is the positive edge now, and all these active edges are marked here. And since J and K are equal to 1, Q0 is going to toggle after every active edge, and starting with 0, it toggles here again, toggles here, and so on. What about Q1? For Q1, Q0 serves as the clock, and therefore we are now looking for an active edge, that is a positive edge in Q0. So these edges serve as the active edges for the second flip-flop, and since J and K are 1 for this flip-flop as well, Q1 will toggle after every active edge. So it toggles at all of these time points, and that is what we get. Now Q1 serves as the clock for the third flip-flop, and therefore we are now looking for positive edges in Q1, and those are marked here. Alright, and once again for FF2, J and K are equal to 1, and therefore Q2 is going to toggle after every active edge. So it's going to toggle here, it's going to toggle here and here. So that is the waveform we get for Q2. Let us now construct the state transition table for this counter. We begin with Q2, Q1, Q0 equal to 0, 0, 0. The next state is 1, 1, 1, followed by 1, 1, 0, then 1 0 1 and so on. So this is the table: 0 0 0 1 1 1 1 1 0 1 0 1 1 0 0, etc. And then finally once again we have 0 0 0 and the counter repeats. Now this is decimal 0, this is decimal 7, this is decimal 6, 5 4 3 2 1 and back to 0. So in other words, we have now got a binary down counter counting down from 111 to 000. There is some homework. Sketch the waveforms, that is clock Q0, Q1, Q2 with time, and tabulate the counter states in each case. What is the difference between these counters and the ones we have seen earlier? In these counters also we have J and K connected together and connected to 1. The clock goes to the first flip-flop. So all these are the same as what we have seen earlier. The difference is here Q bar of the first flip-flop serves as the clock for the second one, and similarly Q bar of the second flip-flop serves as the clock for the third one, and the same thing happens here as well. So work out these waveforms and then you will figure out whether the counter is an up counter or a down counter. We have seen a binary up counter. We have also seen a binary down counter. It turns out that we can combine up counting and down counting into a single counter, and that is what is shown over here. Let us see how this circuit works. First, let us note that there are many features which are common with the circuits we have seen earlier. For example, this J and K are connected together for each flip-flop and they are all connected to 1. The clock goes to the first flip-flop, and in this circuit we have an additional input called M or mode, and here is mode bar. Let us consider the case that M is 1 first. In that case M bar is 0 and the output of this AND gate is then 0, and therefore this clock for FF1 is the same as Q0 in that case, and similarly we will find that this clock for FF2 is the same as Q1. And with these conditions we get the counter circuit that we have already seen earlier, and that is the operation of that counter, that is up counting. Let us now consider the case that M is 0. If M is 0, M bar is 1, of course. The output of this AND gate is simply Q bar of FF0. Now since M is 0, the output of this AND gate is 0, and therefore the clock for FF1 is the same as Q bar of FF0, and similarly the clock for FF2 is the same as Q bar of FF1. And with these connections you should verify that we get these waveforms here, and that is down counting. So in summary, when mode is 1, the counter counts up, else it counts down, and the circuit file is available. You can try out this simulation. So far we have considered counters in which the direct set and direct reset inputs were inactive. That means SD and RD in this figure were equal to 0, and therefore all the flip-flops operated normally without any interference from the direct inputs. It is possible to use these direct set and reset inputs to our advantage to make up counters with the desired sequence. And here is an example. This circuit is a decade counter. That means it will count from decimal 0, decimal 1, decimal 2 all the way up to decimal 9 and then back to 0. So that is the operation that this counter performs, and let us see how it works. Let us imagine that the SD and RD inputs are inactive and see what circuit we have got in that case. So J and K are tied together for each flip-flop and connected to 1. The clock goes to the first flip-flop, whose output is connected to the clock of the second flip-flop, and so on, like that. And this is a circuit we have already seen earlier, and it is a binary up counter. So it is going to count from Q3, Q2, Q1, Q0 equal to 0, 0, 0, 0, then 0, 0, 0, 1, then 0, 0, 1, 0, etc. all the way up to 1, 1, 1, 1. Now the idea is not to allow the counter to go all the way up to 1, 1, 1, 1, but when it reaches 1, 0, 0, 1, then make sure that the next state is not 1, 0, 1, 0, but 0, 0, 0, 0. If we can do that, then we have the desired functionality. That means the counter will count from decimal 0, decimal 1 all the way up to decimal 9 and then back to 0. And that is what we want to achieve with the SD and RD inputs. So let us now look at the connections. SD is 0 for all of these flip-flops, and RD is coming from the output of this gate. And what are the inputs to this gate? One input is Q3, the other input is Q1. So this Q3, Q1 is connected as RD for all of these flip-flops. Now let us look at the SD and RD values for the flip-flops for each of these states. Now SD is always 0 and RD comes from this gate, which is Q3, Q1. Alright. Now consider the first state 0, 0, 0, 0. Q3 is 0, Q1 is 0. So therefore this output is 0. So we have SD equal to 0, RD equal to 0 for each flip-flop. The counter will function normally and goes to the next state. Alright, once again we have Q3, Q1 equal to 0 and the counter goes to the next state. Again Q3 ANDed with Q1 is 0 and we go to the next state, and so on. So this continues. And what is the condition for the output of this gate to become 1? That is Q3 equal to 1 and Q1 equal to 1. And that does not happen anywhere here. And after this state 1, 0, 0, 1, the counter would try to go to 1, 0, 1, 0, and that is when this output becomes 1. When that happens, SD is 0, RD is 1 for all flip-flops, and they get reset. That means all of these Qs, Q3, Q2, Q1, Q0 will become 0 as shown over here. And after this state, the counter simply repeats what it did earlier. That means from 0, 0, 0, 0, it will go to 0, 0, 0, 1, then to 0, 0, 1, 0, and so on. So we have got the desired functionality, and now let us look at the waveforms. So we start with Q3, Q2, Q1, Q0 equal to 0, 0, 0, 0. The next state is 0, 0, 0, 1, then 0, 0, 1, 0, and so on, as in this table. and finally we come to 1 0 0 1. That corresponds to this entry in the table, this one. After this, the counter would try to go to 1 0 1 0, but as soon as that happens, the output of this AND gate becomes 1 and all flip-flops are cleared. And if you notice, there is this short spike here in Q1, and that happens because Q1 is trying to go to 1, and as soon as that happens, all the flip-flops get reset to 0 and we are back to 0 0 0 0. Alright, so that is how this counter operates. The circuit file is given here, so you can run the simulation and take a look at the results as well. Alright, so here is the summary. When the counter reaches Q3, Q2, Q1, Q0 equal to 1 0 1 0, that is decimal 10, Q3, Q1 becomes equal to 1 and the flip-flops are cleared to 0 0 0 0. So that means this state is never reached, and therefore the counter counts from 0 0 0 0 decimal 0 to 1 0 0 1 decimal 9, and that's why it is called a decade counter. Let us now look at a synchronous counter. What is the meaning of this term? That means the same clock is going to all the flip-flops in the counter. Since all flip-flops are driven by the same clock, the counter is called a synchronous counter. Alright, now let us figure out the connections. First of all, they have the same clock. The J and K inputs are tied together for each of these flip-flops. For the first flip-flop, J and K are connected to 1. For the second flip-flop, J and K are connected to Q0 ANDed with 1, that is simply Q0. For the third flip-flop, J and K are connected to AND of Q1 and Q0, so that is Q1 Q0. And for the last flip-flop, J and K are connected to Q2 ANDed with Q1 Q0, so that means Q2 Q1 Q0. So let us summarize. We have J0 equal to K0 equal to 1, J1 equal to K1 equal to Q0, J2 equal to K2 equal to Q1 Q0, J3 equal to K3 equal to Q2 Q1 Q0. Let us now figure out how this counter works. Since the same clock is applied to all flip-flops, they all respond to the same active edge, and the active edges are marked over here, the negative edges of the clock, since these are negative edge triggered flip-flops. And let us now start with the first flip-flop, that is FF0. Now for this one, we have J equal to K equal to 1, and therefore it is going to toggle every time there is an active edge. So if we start with Q0 equal to 0, it's going to toggle here, go to 1, toggle again, and so on. So that is what we have for Q0. Next, let us look at Q1. Now for Q1, J is equal to K, and that is equal to Q0. So we need to look at Q0 just before the active edge. Before the first active edge, Q0 is 0. That means we have J equal to K equal to 0. And so therefore, if Q1 was 0 here, it's going to continue to be 0 all the way up to here. Now when this active edge arrives, we look at Q0 just before that active edge, and we find that it is 1. So therefore Q1 is going to toggle at this point. When the next active edge arrives, we look at Q0 just before that, we find that it is 0. So therefore no change in Q1 at this point, and so on. So in this way we can figure out what's going to happen to Q1, and this is the result. Let us look at Q2 now. For Q2 we need to look at J2 equal to K2 equal to Q1 Q0. So we need to look at this function just prior to the active edge. If that function is 0, then there would be no change in Q2. If it is 1, then Q2 is going to toggle. Alright, so let us say Q2 is 0 in the beginning. At this point, just before the first edge, Q1 Q0 is 0, so no change. At this point, again Q1 Q0 is 0, so no change. At this point, Q1 Q0 continues to be 0, no change. At this point, Q1 is 1, Q0 is also 1, so therefore Q1 Q0 is now equal to 1, and therefore Q2 is going to toggle over here. So this way we can continue and figure out what's going to happen to Q2, and this is the result. We can follow the same procedure for Q3, and now we need to look at J3 equal to K3 equal to Q2 Q1 Q0. When this function is 1, then Q3 is going to toggle, otherwise Q3 is going to continue with its previous value. Alright, now let us look at when this becomes 1, and when we see these waveforms we figure that it's going to be 1 here because Q2 is 1, Q1 is 1, and Q0 is 1 here, and also it's going to be 1 over here. So Q3 is going to toggle at this point and also at this point, and otherwise it's not going to change. So if we start with Q3 equal to 0, it's going to stay 0 here, toggle to 1, and then back to 0, like that. So what kind of counter have we got? From the waveforms we see that it is a binary up counter. So we have 0 0 0 0, 0 0 0 1, then 0 0 1 0, and so on all the way up to 1 1 1 1, and then back to 0 0 0 0. So it is a binary up counter counting from decimal 0 to decimal 15, and we have seen this kind of binary up counter earlier. The difference is that we have a synchronous counter here. That means the same clock is going to all the flip-flops. To summarize, we have looked at a few counters in this class. We have seen an example of a synchronous counter. In the next class, we will see how to design a synchronous counter for a specific state transition table. See you next time.